Hello everyone. Welcome to our battery talk with our brilliant advisor Richard Fields. I'm Hakan. I'm co-president and electronics team advisor in Hyperloop Manchester team, which is a student-led team aiming to build a small-scale Hyperloop pod and share our knowledge with people around the world. So today, this talk is our one of the first steps to share our knowledge with the people. So it's a precious moment right now. So thank you, Richard, for accepting to be our advisor and helping us along the way so far. So now I'm giving the mic to you to delve into the battery world. So floor is yours, Richard.
All right. Thank you very much, Hakan. Thank you very much for having me here. And I will just check. Oh, there we go. Let's go back. There we go. Just as a quick introduction to myself, I've been working with Hyperloop Manchester for just under a year now, I think, since they kind of formed. But a bit more about myself is I've got a background, a PhD in material science, where I worked on battery technology, kind of fusing batteries and supercapacitors together. I've also got a master's in aerospace engineering, and I've worked on small satellites and these kinds of things in startup companies. I'm also a bit of a tinkerer with equipment, electronics, systems, software. Kind of throw anything at me and I'll kind of just take it apart and have a look at how it works, I guess. And I also have recently started building companies. Essentially, I consider myself to be a venture builder. I'm now on to my third company at the moment. In the picture there actually is one of the first ones, which was advanced microstructures. And if you look very closely on the screen on the laptop on the table, you can see some levitating droplets. I it built like a little acoustic levitator for structuring and manipulating 2D materials, but that's kind of old history. So let's go on to this, the talk. So today it's going to be a webinar on kind of how batteries work. That's going to be about the first 10-15 minutes. Then how batteries are best used, how they can be applied, and then on to how batteries are made and what the future might look like for that. But it's not just about structure here. I'm really aiming to transfer knowledge to you, to all of you here who've joined and attended. So I want to transfer an understanding of that there are different battery types that you should consider when you're thinking about using energy storage devices. Familiarity with battery specifications and the real world implications they have, so that you can make more informed choices when selecting the right battery for your kind of task, for your application. And then just kind of the beauty of battery design and development, because I think it's fantastic and it's amazing. So jumping straight in, these are the core components of a battery. There's the current collector on either side. There's the anode, which is the negative electrode, and the cathode, which is the positive electrode. And in the middle, in between these, is an electrolyte, often a liquid type material. And there's also a separator material, which is non-conductive, at least electronically, and it stops the anode from touching the cathode. And that between these two, the anode and the cathode, there's a potential difference, which is known as the voltage. And this can drive electronic devices as electrons flow around a circuit once a circuit is completed and they travel from one side to the other. Okay, yeah. So here's a more visual representation of that. On the left, you can see, so just focusing on the left, you can see the charge mechanism, whereby you start with a discharged cell. So in this case, this is actually a lithium-ion battery. So those purple particles are lithium ions, and the things that are moving around on the top are electrons. And you start with electrons and lithium over on the left-hand side on the cathode. And when you polarize the cell to kind of apply a potential across it, you'll charge the battery to make the electrons transfer around to the anode, and the lithium follows suit. The lithium kind of shuffles over and joins onto it. But then if you jump over onto the right-hand side, you can see the discharge the reverse of the battery. Soon when you apply, put it into an application, you complete a circuit, maybe powering your phone or a car or anything, the electrons flow back through the circuit and provide charge and energy to the system. And in return, the lithium ions move back across to the left-hand side. So it's important to remember that this is a physical phenomenon. There are real physical kind of atomic particles that are moving around, and also subatomic particles, which are the electrons, but they're actually physically moving around and they're having to be absorbed within solid substances. But I'll introduce that a little bit more on the next one. So in order to understand this in a little bit more detail, I'm going to give you a very high-level overview of fundamental electrochemistry. So electrochemistry is it's electrical chemistry. So you're moving charge. Electronic kind of actions are ones involving electrons. But in this case here, what you can see in front of you are ions. These are actually the positive and negative particles which form salts. General everyday salts are formed with structures just like these. On the left-hand side, you can see a positive particle, and you can tell it's positive. Oh yeah, the way this is visualized is it's an electrostatic potential map. So this is like the surface of the particle and its charge distribution across the surface. So how that particle is charged. And you can see on the outer surface, the outermost surface, it's positive on the left-hand side, and on the right-hand side, it's negative on the outer surface. And that would actually cause these two particles to want to come and connect together. They would sort of slot in. The blue part would come up to the red part and they would attach. But when you have more complex surfaces, like are shown on the left and right, particles can come up to the surface and they can sit there and interact with it. They can become part of it. But if the potential is high enough, or the structure of the particle is high enough, they can be absorbed onto the surface, and they actually then form a larger electronic structure, a single larger electronic structure. And yeah, that's basically how charge and particles behave at this sort of scale. These are the fundamental smaller scale of them. Although a lithium ion, which isn't shown here, is actually just one block of it. I've got people popping in. Okay, so to to apply that in a more so you've got those charged particles, positive and negatively charged particles, and they're attracted to one another. And these are the building blocks of energy storage systems, and these are the mechanisms by which those charged particles interact and store energy. So starting with a very simple one, a capacitive charge storage mechanism. In this case, it's actually a purely physical phenomenon. There isn't a chemical reaction that's going on. Things aren't becoming sort of chemically bonded to form a single structure. They're just being absorbed onto a surface. In this case here, what you're seeing is a positive red surface, which is getting polarized. It's got a high potential. And then the negative ions, the blue ions, are being attracted towards the surface. And just like in a traditional kind of capacitor where you have maybe two metal plates, hopefully most of you have seen that kind of idea. It's the same thing that happens, but at the kind of atomic level. And this actually creates the building block of what's known as a supercapacitor, because it's very small, tiny particles. And if you give it a high surface area material, then there's a lot of surface to store charge on. So that becomes quite powerful and a lot of energy to store. But then there's another type of charge storage mechanism which behaves similarly to capacitive charge storage. And I'll show you an example of how they actually behave and look sort of in a second in terms of voltage. But in a pseudo-capacitive system, the ions are drawn into a structure and they're sort of loosely bonded with the surface of that structure. They don't actually bond deep inside of the atomic structure. They just go in between the cracks, basically, in a physical way. But the response, if you charged and discharged it and look at the voltage profile, it would look similar to a capacitive, which, yeah, I'll show you what they look like in a second. Then there's an intercalation type charge storage. Now, this is actually one of the building blocks, ways, the building block of lithium-ion batteries. In the middle here, you can see lithium ions, which are sitting in between graphite rings or graphite sheets. And this is where lithium has entered in from an external surface and then penetrated into the material and started to become stable within its structure. Not many materials and many elements can do this, but yeah, the ones that can, they accept lithium inside. Yeah, I'll go on to a little bit more about kind of the degradation of how this might happen later on. If you just remember that particles sit inside of another structure, it'll become important later. And finally, there's an extra charge storage mechanism, which is metal plating, where you're essentially depositing materials on top of each other. They just coalesce and join together because they like the same material, and they build up a larger and larger layer of that material. And this, if uncontrolled, actually leads to sort of dendrites and particles forming or coming out from the surface. We can pierce the separator and short circuit the cell. So it's actually a trick, or you have to finely balance and control the cell to make sure that you don't initiate the wrong charge storage mechanism, or you go past the limit and you might end up breaking the cell. But to give you another idea of how those different charge storage mechanisms can be combined, this is what forms different types of energy storage devices. So in the top right, you have a carbon, this is a carbon material, a black carbon material, and that would actually form the basis of a supercapacitor, where you're forming electrical double layers on both surfaces of the carbon material. Both the positive ions in the middle would go to the negative electrode, and the negative ions in the middle would go to the positive electrode. And the same would happen on the pseudocapacitive material. But when you get to this sort of symmetric battery type material, the intercalation materials, then ions and materials are transferred over from one side to the other. And I've just noticed it says negative on both sides here, which is not right. One side should be positive. But ions are moved over from one side to the other. And then you can have asymmetric materials as well. And these are the structures that form sort of newer energy storage device types, such as lithium-ion capacitors, where you've got half of a supercapacitor and half of a battery. In this case, I think this one here, the positive half is a supercapacitor type material and the negative side is a battery type material. And you're combining the system to get benefits from different electrodes. So, for example, in this, because the supercapacitor system is purely physical, the charge storage mechanism is very quick and very fast, so they become very powerful devices. But in the battery type material, the charge storage mechanism requires a chemical reaction, which takes time, and it can be quite slow. It takes time for materials to travel deeper into the material structure. So by combining them together, you can actually create hybrid devices, which are more powerful and higher energy density. So you get interesting stuff out of that. Now I was talking a little bit earlier about what they actually look like in terms of their profile, the charge-discharge profile. So this is a plot of the cell potential up on the top, and then just time or charge that's been transferred along the bottom. The black line here shows a capacitor, and this is where you've got the buildup of charge on the surface. As the surface becomes more charged, the voltage increases because there's a bit more sort of resistance to more charge being added. So you have to apply a higher voltage to increase that charge. And if any of you have ever charged a capacitor and then stopped charging it, you actually find that it discharges quite quickly because there isn't a chemical reaction that's holding the charge statically to the surface. This isn't true in all types of capacitors. Supercapacitors can hold their charge for a few days, perhaps, maybe a week, perhaps, and then after that they discharge. And it's mainly because there's no chemical bond that's holding energy in place. In contrast to this, there's the battery, which is the dotted line going along here. And this shows a profile, a plateau, where you start charging the cell and then it starts accepting ions into the structure, the lithium ions in the lithium-ion battery, into the structure of the material. And that happens at a constant potential. They just keep shuffling deeper down into the structure, and you hold the cell at that potential, and they keep on shuffling in until it starts to get full. And when it does start to get full, then it takes a little bit more charge just to kind of fill up the brim, especially really near the surface, or to make sure that lithium gets into all the kind of the pockets and sites, the charge storage sites that it can get to. Another part that you might notice here on the discharge is a similar effect. You start with the voltage decreasing and then it plateaus. But there's also to notice in this is a potential difference, the voltage drop between the charge and the discharge. So when you charge your cell, you actually charge at a higher voltage than what it will discharge at. And this is because of sort of the thermodynamics of the system. You have to have some energy barriers and also resistance, just generally resistance in the cell. Same with the capacitor up here. You've got this equivalent series resistance of an energy storage device, and that will be the resistance towards discharging. So kind of going on to what those cells, what those materials look like. I just showed you a profile of the voltage profile of batteries and capacitors, but this is to give you an idea of how those cell types and those configurations relate to power and energy. This is a plot. It's called a Ragone or a Ragone plot. And on it, you can see the specific power. So that's the power per weight, or power per kilogram, and the specific energy, which is the energy per kilogram. And it shows different types of energy storage devices. So there's traditional kind of capacitors up in the top left, where you've got two metal plates opposing each other, or even sort of the kinds of capacitors used in electronics, standard electronics. Then you have EDLC, so this is electrical double layer capacitors, the ones that have like high surface area particles, and they have quite high power density up here, but lower energy density. Alongside these, you've got the nickel metal hydride and then rechargeable lithium-ion batteries. Both of these are kind of rechargeable systems. And then you've got what's known as a lithium primary battery, which is a non-rechargeable battery that has the highest energy density out of the ones shown here. Slightly lower power density than some, but the most important part is that you can't really recharge that. It often comes as a watch battery, like a 3-volt watch battery. There are reasons why you can't recharge it. You can ask me that later on if you like. Then there's some examples of other types of systems that are shown up here as well. There's pseudo-capacitive devices, hybrid activated carbon and pseudo-capacitive, and this a lithium-ion capacitor up in the top here. So you see that different cell types give you different performance. So you might want to select the right one for the application you're using. Another aspect of this is, so it's not just about energy and it's not just about power, it's also how long you can use that battery for. In the case of a primary battery, you get one cycle out of it. You don't even get a cycle, it's half a cycle. But in rechargeable batteries, you get the cycle life of it. That's how many times you can reuse it before the battery degrades beyond a certain usable capacity or energy storage capability, or before the resistance is too high. This is an example here which is shown for a lead acid battery, which is actually quite an extreme example of degradation, but it relates to the depth of discharge, so how deeply you discharge the battery from its full capacity, or from any capacity really. It doesn't have to be from full, but in this case it is from full, versus the expected average cycles of that. In this lead acid battery, it degrades, if you discharge to 100%, you can see your battery's only going to last a few hundreds of cycles. This isn't true for other types of chemistries like a lithium-ion battery, especially when it's well optimized and balanced as a cell. Instead, you would end up with a shallower decrease or degradation, but the similar phenomenon still exists. The deeper you discharge your battery, or the more of the capacity you use of the battery, the faster it's going to degrade. Then there are also sort of specific application specifications related that are application dependent. So if you're working in different temperatures or having batteries in different temperatures, again, there's cycle life on the bottom and the capacity retention on the top. And the room temperature one lasts sort of much longer. It retains its capacity than when you go down to 60, 80 or 100 degrees C. This is because you're sort of giving more energy for adverse reactions to occur inside of the cell. So as a kind of a fundamental explanation of it, something you can do to prevent this is keeping the battery cool, giving it a cooling system, either liquid cooling or air cooling, or you can make sure you offload high current, any high current work onto a different type of battery that's better suited towards high temperature. So you could have two different batteries, one for, well, they'll both be high temperature, but one will be operating at a higher temperature because it's getting more current pumped into it. It's a little bit too much detail at this point. Then there's also cell balancing. So if you're building a pack or a module, you want to make sure that your cells are not exceeding their maximum voltage. So, and this would happen if you've got multiple cells in series and you're charging all of them, but one of them is starting to die or to break, then the other cells will kind of compensate for that and accept more charge and become overcharged, and then they degrade much faster as well. So here you can see a standard kind of operating voltage at 4.2, and it slowly decreases the number of cycle life, the cycles that you can achieve as the voltage is even just pushed over by 0.05 volts. So it's kind of really core if you're building a system with multiple cells or cells linked in series, that you do load balancing or cell balancing on the system. And then another aspect of kind of selecting the right batteries is the price per kilowatt hour. You want to make sure that you're kind of getting it at the right price point. Now here is really actually a general overview of the kilowatt hour, the price per kilowatt hour of lithium-ion batteries in general. Different battery types have different costs. Lead acid batteries are actually kind of cheap compared to lithium-ion batteries, but because they're not as energy dense, maybe you need more space for them. So there are other sort of aspects you need to consider when costing all that up. But these two plots show quite an interesting trend. Over the past few years, the price of batteries per kilowatt hour has dropped significantly, but it has been kind of noted by automotive makers such as Tesla that the price hasn't dropped fast enough, or isn't going to drop fast enough. And it's not really dropping fast enough. It's just that no one's pushing it to drop faster. The bigger technical gains were harder to achieve. But I'll discuss later on and show you how they're really looking to drive the cost down. These are actually at equivalent times in 2014, more or less over there. I think they're going to be bringing what would have been a 62 kilowatt hour battery in 2030 back to 2023, 2024, something like this. So I'll talk about that a little bit later on. But just for now, there is a 1 minute break, just so I can have a sip of water. And if anyone has questions, can you just like write them into the chat now? And then like from this section, from what I've talked about so far, and then we can review it again like at the end. So just 1 minute. Okay, I just had a quick question from Hack, who's here, and there's also Gus. There's one about high quality supercapacitors available in the market now. I would say yes. The sort of market leader in this is Skeleton Technologies, and there are also multiple others. And there's also these lithium-ion capacitors in the market as well. So yeah, recommend going and have a look at them. And there's another one as well, Maxwell, who were bought by Tesla. They also make supercapacitors. I can imagine that Tesla are looking to hybridize their drivetrain. So you've got supercapacitors for high-speed acceleration and then batteries for cruise, so you can offset the current. And then I've got another question there from Gus. With regards to temperature, the lower the better, or is there an optimal operational temperature? There is an optimal operational temperature. If you go too low, then the electrolyte starts to potentially freeze or become sluggish. So different chemistries you can tweak them by putting additives into the electrolyte, slightly change the salt composition, and they will give you a different optimal operational temperature. Maybe most of them are designed to be like room temperature, 20 degrees, but some are designed to go from -40 up to 60, more or less. Some are very high temperature. Yeah, good question. Okay, so we'll keep on going. So the next, has this worked? Yeah. So the next part of this is to really delve into how batteries are made, why they look the way they do, why they perform the way they do. Not really why they perform, just why they look the way they do, and how to manufacture them. In case any of you want to make a battery at home. So these are some examples of cell geometries, different shapes. Most of you know the cylindrical type, so this is AA type batteries. There's also a larger variety of this, the 18650 and then 2170 and what's Tesla one? New one, the 4640, something like this. Maybe that wasn't right, but it's a much larger cell. And then there are another type of cell which isn't cylindrical. It's a pouch cell. This is sealed in laminated aluminium foil. It's essentially like glorified crisp packet material. So it's very thin, and you seal it at the edges by heat sealing it, sort of sandwiching it between two heaters. There's then a sort of prismatic type cell. This is a very basic prismatic cell, I guess, but there are larger ones which are in metal cans. And then you've got coin cells, or little button cells down at the bottom. And beyond that, you've got sort of very novel types of cell geometries. You can have, if you've got the electrode materials are all flexible, or you've got enough flexibility in the cell, then you can make a flexible battery. Here's one that can ripple. And on the right, if you use a laminated, this pouch material, you can actually seal in any shape you want, even with a hole in the center. I would give a good shout out to one of my colleagues at the University of Manchester who made a Christmas tree shaped battery and then put little LED lights across all the edges so they all lit up. That one looked amazing. But looking at actually what's on the inside of those batteries. So on the top left, you've got a straight stack, which is what you'd use in a pouch cell, really. Well, in some types of pouch cell. You're just layering the material. So negative electrode, positive electrode, separator, negative electrode, current collector, and then having tabs on kind of alternating sides so that you can connect to them, or even on other ends of the battery so that you can connect to them. That's what the I-Pace has. It has two metallic tabs at either end. And this is the Jaguar I-Pace car. Their battery packs are all pouch cells. But then you've got the Swiss roll type system, which is what you'd use for a cylindrical cell. You just take the materials, lay them all up on a big long sheet, the positive electrode, the separator, the negative electrode, and just roll them all up and then stick them inside a can. Then you've also got two different ways of folding the materials together with the separator. These actually result in a cell which would look similar to the straight stack, but they can be a little bit quicker to manufacture. This one, the wrap and fold, isn't actually used in production because you can see that you end up with excess separator all around the outsides, which means you have to put more electrolyte in, it becomes heavier, and it's not a great configuration for a cell. Whereas this Z folding, where you just crease the materials and sandwich them together like an accordion, this is one of the most kind of commonly used ways for making pouch cell type materials. And then, so this is then onto battery manufacturing. So you just saw the shapes and the ways in which those materials can be joined up, but just stepping before that and looking at how you actually manufacture those materials. So there's a couple of processes in this. You start with making a slurry. So you'd do this separately for both the anode and cathode, for the positive and negative electrodes. You'd make those separately as slurries, and they start with powders that you put into a pot and mix them all up. Then you take that slurry and coat it and dry it. You'd coat it onto some aluminium foil, and I'll show you examples of these in a little moment. Well, it doesn't have to be aluminium foil, it could be copper foil as well. It depends on what the chemistry requires. Then you calender and compact those coatings to make sure they've got the right density. And there's a bit of an art to doing this so that you don't over compact the electrode materials, so you basically crush them and end up with no sort of room for electrolyte to penetrate into it. You kind of would you'd make a very thick and it wouldn't be able to soak up electrolyte inside of it. So that could be a problem. So there's a trick towards getting that at the right density. Then once you've compacted those materials, you cut them all up into the right shapes. So you saw there, you can see the stencils that have been stamped out. And then you layer them up in whichever kind of geometry that you're looking for. This is in a stack. And then you'd put them inside of the casing or the cell sealing and fill it with electrolyte. And then you do a formation cycle. I will run through kind of each of these a little bit more so you get a bit of a deeper understanding of what they actually look like at different scales of battery development or different stages. So this is an example of slurry preparation. Over on the left, you can see what's known as a dual axis asymmetric centrifuge. I think it's a DAC. And basically you put your materials inside of this and it spins it around in two different ways and you end up with a nice sort of mixing process. you can end up with a good, nicely uniform slurry. But it's relatively small scale. You don't get many of these that are so large. Then you go into more of a pilot scale production, and you've got these kind of vortex mixers and maybe some high shear blades in there as well that kind of chop up the particles and mix everything all together. And this is kind of a medium to high scale production. And then if you're going to go and build a gigafactory, then you might want to go for continuous production of slurry, where you'll be continually dosing powders and liquids into the hopper and feeding it in. And this shaft down here has sort of rotating and interlocking screws that grind the materials and extrude them and force them out and mix them up very well. Part of the challenge in this is actually taking research and work from the laboratory scale and taking it all the way up to a continuous industrial production. Each of these scales actually result in a slightly different slurry. So if you design the perfect cell at the lab scale and then try and take it directly to the continuous industrial scale, you're going to find that it doesn't quite work, even though you've used the same recipe, the same ratios, and all of this. So this is one of the kind of the major hindrances towards doing research and development. And especially if you want to test something at a continuous industrial production, then you're going to be using tons of material, but you're not yet certain if that process is going to work out right. So it's a bit tricky to do that. And there's kind of the place that's going to be investigating this in the UK is the UK BIC, the UK Battery Industrialisation Centre. It's based down in Warwick or Coventry. They're also going to be looking at all of these aspects, I guess. Then you go into slurry coating. So you've just made your slurry, you've done the mixing. Over in the left here is a laboratory scale slurry coating process where you get this doctor blade down here, or it's a gap applicator, and that's pushed down a sheet of foil using a bar as a pusher, and then you're left with a thin coating which can then be dried. A larger scale, a pilot scale version of this is where you'd have a roll-to-roll system feeding through. There's an oven at the back here, and the coating, sort of a gravure coating head here, which is again similar to a gap applicator. It's just got a thin gap that you're passing the material through, and this you'd either be adding slurry into this and you'd run it until the foil runs out, and the ovens are kept at like 60 degrees. You'd be looking to get, I don't know, only 5 meters per minute of production out of this, like 5 meters of coating per minute. But then you go to these really big systems, and these are really cool. And they're big long ovens. It's about 50 meter long, ginormous spools of aluminium foil and copper foil, and they're doing the feeding and the coating at this end. The material is shooting through to the other end, and I think they do try and aim for like 50 meters a minute. So I think it takes about a minute for material to pass through here and then end up being coated onto these strips, which will then be processed later on in the next steps. So speaking of those next steps, the main ones really are the calendaring and the slitting. Calendaring is kind of, as it suggests, just compacting the materials down between two rollers typically. These can be heated or just at room temperature, depending on what sort of rheological sort of properties it has. So like the viscosity, not really the viscosity, but the performance of the material, the binders maybe that you've used inside. And then after you've calendared them, you can slit the materials down to the shapes and sizes that you want that'll be suitable for the electrodes or the batteries that they're going into. Then it goes on to cell assembly. This hasn't got so much detail here, but the main one in the middle is actually this pouch cell assembly. This is done by hand. This isn't how they do it in industrial systems, but in principle it's the same. You have a vacuum chamber a vacuum chamber with a heated element at the top, and the lid would come down, it would pull a vacuum inside of the cell, and then these jaws, these heated jaws would come down together and seal the edge of the cell. And because you sealed it under vacuum, when you return the system or the cell to ambient pressure, you've then got atmospheric pressure pushing down on the cell and sort of forcing it together and compacting it. That's for a pouch cell. Then a coin cell is you've got the cap and the can, and you've got all the materials inside. You also have a spring and a spacer inside, and these are then crimped. So the outer edge of the can is folded around the top part of the cap, but it's done in a way so they don't short circuit because of the gasket. And this leads to your watch batteries. And then you've got a cylindrical cell over on the right, which is you've wound everything up like in the jelly roll, and you slot all of those components in. You make sure you've got contacts down to the tab onto the material so that you can contact one of the electrodes. And I'll talk about one of the innovations there in a second. But that's it. It's basically just slotted into a can, and this rim is also crimped, so it's just folded over in on itself to seal the cell. But after all this, there's a sort of final stage where you have to do, so once you've done the manufacturing of it, you're not yet finished in making batteries. You have to do something called formation cycling, which is where you charge the cell under specific conditions. They could be under different temperatures or up to certain voltages, and you're holding the cell in those conditions, or I don't know, cycling the cell in between those conditions for a few hours or a few cycles. This actually requires quite a lot of energy to do. You have to basically be charging every single cell that comes out of the battery, out of a factory, I don't know, for a couple of times, 4 or 5 times at least, I guess. But the main reason you're doing this is to form this solid electrolyte interface. This is a layer that's formed on the materials inside of the battery, and essentially it's like preferential corrosion. So you're pre-corroding the materials in a way that stops them being degraded in a more detrimental way to the longevity of the cell, and you do it under certain conditions. And this is really driven by adding certain additives into the electrolyte, so additional salts or solvents that go inside of the system, and these form a preferred SEI layer, and that helps keep the battery cycling for a long time, unless it gets broken, which can happen for certain reasons. Just to kind of give I don't know if this is going to work. Oh, maybe it's not. I wanted to show you a video, but for some reason it won't let me show the video here. It was actually of a complete system that I built last year with some friends from over in California, and well, they're actually from all over Europe really. We started a company together, and we built a proof of concept system that was compact and desktop based, that would seal that would prepare batteries for us. But unfortunately the video isn't working. If you maybe we can find it again. If you drop me a message, we can have a look at it then. Oh, it is working. Oh, there we go. Crazy. So this is this is it. There's a compact automated cell assembly system that you missed maybe the first parts, but it was coating and punching, and there isn't a calendaring system on this, but it was building these sort of small pouch cells as test cells. Great. So now I'm just going to jump on to sort of the innovations that are happening in this space, in terms of the battery technology space. So you may have heard me mention in this that you have tabs on batteries. On both cylindrical batteries and pouch batteries, you have to have a tab, which one of them is connected to the negative electrode, one of them is connected to the positive electrode, and these let you connect to the main, the larger kind of electrode coating or the roll inside. On the left, you can see the traditional way of doing this, which would have been to put a single tab on each, the positive and the negative electrode, at sort of either the beginning or the end of the roll, and that tab would have then fed current all the way round and through to the rest of the roll. And it was kind of realized that this isn't a very efficient way of transferring charge to a large system, especially when it's so tightly wound. So what sort of the scientists and researchers at Tesla have done is they've created a folded tab edge so that the entire part of the roll can be folded over on one side. In this case, it's just the anode that's been folded over, and on the opposite side, I presume they would have the same, but for the cathode. And this means that you can transfer charge now to every part of the coating all at once, rather than going down a little tab and then having the current or the charge transfer around the rest of the winding. So it increases it reduces the resistivity of the cell, so that increases the power capability. And because you've increased or decreased the resistivity, you've also decreased the thermal output of the cell. So the cell won't get as hot, you won't waste as much energy, you won't have to have as big a cooling system for that type of battery. So it's quite a nice design, and it'll save weight on like a pack or a module scale. And it was a purely mechanical change to the way that batteries are made. There's no fundamental sort of chemistry that's changed. Another sort of engineering approach to improving batteries that's started to be deployed is to use what's known as a polar series connection. So in a traditional cell, or in a traditional sort of pack, you would connect cells together by having one terminal feed, so the positive terminal would then connect to the negative terminal of the next cell, and then that would then, the positive of the next cell would connect to the negative of the next cell, and you would be stacking all these cells up together by using sort of external bus bars between the cells. But these add weight, and really all they do is just transfer charge from one cell to another. So instead of having those sort of bus bars externally, what people are doing or planning to design now are cells where they put those bus bars internally inside of a cell. And what this means is that you can stack cell components on top of one another. So you could have a 3.6 volt cell here, 3.6 volt here, 3.6 here, and you'd end up with about 12 volts in total across the whole lot. But you've only got these two external contacts on the outer sides. There isn't any extra wiring or connections that have to go on the outside. So that can significantly reduce the weight of designing a pack, because you don't have all this called like gubbins inside of a car, all this extra cabling that's now not needed. So you can save, I think it's about 20 or 25% of the mass of a pack just by changing the way the pack is built, or the way the cell is built. Although you don't actually change the energy density itself, you're just changing the pack energy density. You don't change the energy density of the cell or the materials. It's got the same amount of materials in both cells. It's just that one doesn't have any extra sort of materials on the outside. So it's challenging to make though. You have to stop materials from leaking, or liquids or gels from leaking around from one cell to another. If that happens, then it's all broken. And it's really difficult to do, but it's definitely coming. This was started in 2016, I think, so it's coming again, it's coming soon. And then a final one, again, sort of on the Tesla side a little bit, is doing dry electrode coating. Now this is really related to the cost of a battery, and also the environmental impact of a battery. Typically, when you do that slurry preparation step and you mix all the materials together, you have to use a solvent inside of that. And they use some nasty solvents typically. And then they capture it and reprocess it and use it again, but it's just not really great using that solvent. So instead, they're starting now, well, companies are starting to use dry electrode processing, where you can put powders directly onto a metal foil without having any liquids involved. And this is still really at the early research scale. I know that Tesla bought Maxwell supercapacitors because they developed this technology, but I know that they're still really in the proof of concept stage, so it's going to be a few years before this gets fully deployed. But again, just by reducing the need for a hazardous and nasty material, you reduce the complexity of a plant and a factory, and that reduces the cost, as a bottom line impact. So those are some ways in which the future of batteries can be affected just by engineering approaches. And now I'm going to do a shameless plug for my own company, which is Accelerate. I'm building a company which is building automated battery technology. We're starting by automating a lot of battery R&D work, which is essentially the way that cells are built at the moment is typically done by hand in an R&D lab, and you end up with a lot of human error, a lot of variability in the cell design or the cell preparation, and these lead to kind of fundamental flaws in decision making later on, or ambiguity and uncertainty, meaning you have to make more cells and repeat processes over and over again. So we're trying to get to better cell configurations faster. So just to plug it a bit further, if anyone's really thinking about what to do next, maybe you're coming out of university, let me know. There might be some positions in the near future to work on automated battery technologies. And great, yeah, I think that's really it. So if anyone, give me a shout out of your questions on here. I'm really happy to answer all of them. I want to say thank you to Hakan and Hyperloop Manchester for putting this all on, and I think their team are doing a really good job. I think they're making interesting technology and pushing sort of the boundary of development. So yeah, you can contact us both down there at our emails as well.